Alright, so let's have this function f defined as like this. So recall that f of xy is defined as this function where a consists of all points xy in R2 such that x is greater than 0 and y is between 0 and x squared. In my write-up for exercise 1-26, I drew a graph of this to sort of show you what it looks like. And here, of course, when I say f of x, y is the indicator function of the set. This means that if x, y is in A, then f of that point is 1. If x, y is not in A, then f of that point is 0. Okay, so fix some vector... fix some vector x in R2. Okay, if x is a 0 vector, then dx f 0, 0 equals 0, so it exists. Otherwise, so that's a trivial case, otherwise if x is not 0, the set of all points tx, where t ranges over all values of r, is a line through the origin and through x, of course. Now, if we go back to 1-26a, we know that every line passing through the origin contains an open interval around the origin, which is entirely contained in a complement. So this line contains an open interval I containing the origin such that I is contained in a complement. So now if we take the derivative of f at the origin in the direction of x, this is by definition the limit as t goes to 0, we have 1 over t, then we have f of tx minus f of 0, 0. So now since we're taking the limit as t goes to 0, we can also assume that t is in I, because if t is small enough, then it's going to be contained in I. Because I is an open interval containing the origin. Oh, well, I guess this should be all as t approaches 0 where tx is in I. And now we still have 1 over t. And now we can evaluate f at tx as just the indicator function of a at tx. And we know that f of 0 is 0 by definition, or just because the origin is not contained in a. Okay. So now we can take this limit, and if we take this limit, then, well, if tx is in I, then tx is not in a. So the indicator function at a of tx is going to be 0, so this is going to be the limit of 0, which is 0. Which obviously exists. So dx f 0, 0 exists for all vectors x in R2. And this is true even though f is not continuous at the origin. And of course, the fact that it's not continuous at the origin is what we proved in exercise 1-26b. And yeah, so this is just another sort of strange example of like weird phenomena that could occur with functions and differentiability, especially if you don't assume like nice continuity and everything. Yeah, because here the function is not even differentiable at the origin. It's differential. Its derivative can be taken in any linear direction at the origin, but of course, as we proved, it's not continuous there because you can approach it. You can approach the origin along the set A. But yeah, so that's how this exercise works, and it's just sort of like a. So the point is, one of the main ideas of mathematical analysis, real analysis, whatever, is that limits are weird, and weird things can happen when you take limits. And the definition of a derivative involves a limit. And so really weird things can happen. So this is just a way for us to like explore a little bit of some of the weird things that can happen with derivatives. And yeah, that's all we need for the exercise, and so we're done.